Hey guys, today we're going to apply the concept of conservation of energy. So we've learned several equations that describe different types of energy like potential energy and kinetic energy and spring energy and so on. And today we're going to take advantage of the idea that energy is energy and see how we can use that idea in equations. So we're going to show you general concepts here first, and then I'll walk you through a couple examples that really kind of show you the power of this concept and why conservation of energy is such a big deal. So let's start by looking here at this worksheet. This is one of the things you have to do. This is mainly just for practice here. Um, and I would like you to do it first because it's the simplest idea and that makes the math easy. So for example here, we have a high diver up at the top of the platform here, diving into a bucket of water. And the idea here is that the total energy of the system never changes. Energy is conserved. So he has 15,000 joules of potential energy at the top, and he's not moving, so the kinetic energy is zero, but the total energy is 15,000. And as he comes down, more and more of his energy is converted into kinetic energy, but the total is always 15,000. Now, um, when he gets to the bottom, there's no potential energy left. It's all kinetic energy. Um, Now, it is possible to figure out how fast he's going if you know his mass, because you know how much energy and um, and you know how much mass he has. So you can just solve that for velocity. And I'll walk you through a problem like that here a little bit later. Here's another one, same kind of idea. The ball has 30 joules of potential energy at the top, and it wants to know how much potential energy it has at the bottom here. So um, it doesn't matter the route that the ball takes to get to the top. All that matters is the elevation here. Okay. And then it asks you some intermediate ones. And then this last one is the idea of, well, what if you rolled it off the end? Well, it's going to all convert into kinetic energy. So again, energy is conserved. Most of these are just like this. The pendulum one down here at the bottom is actually a pretty revealing one and a significant one. You've probably never thought of a pendulum this way before, but a pendulum is continuously converting potential energy into kinetic energy and back again. So the pendulum is as high as it can go. It's at the top of its swing. It stops for a moment there. So it has zero kinetic energy, and all the energy it has is potential. And then it goes faster and faster and starts to convert that energy into kinetic. And when it's at the very bottom of its swing, it's all kinetic and there's no potential. And then it converts it back into potential again. So the total energy is always the same, but the pendulum is continually transforming it from kinetic to potential and back again. Okay, let's see. The other ones are the same idea here. The only one that doesn't fall into this theme is this one here about the cars and what happens to the kinetic energy as this velocity increases. So in this one, the energy is not conserved because the car is going faster and faster. But I would like you to run the numbers here to figure out what happens to the kinetic energy as you double the speed from 30 to 60 and as you triple the speed from 30 to 90. Okay, don't shoot from the hip on that one. Actually dive into the equations and see what happens with this one. Okay, so basically everything on this worksheet is conservation of energy except for this one. And I do want to see you get the right answers on this one. So actually plug in some values. Okay, so let me give you some examples of how we can use this idea of conservation of energy. Essentially, you set different equations equal to each other and then solve for the variable that you want to solve for. So for example, if you have a spring that is all coiled up, the spring energy, as you know, is 1/2 kx squared. So that describes the energy in the spring. And if you're given enough information to figure out exactly how much energy is in the spring, well, great. Then they'll ask you, okay, well, when the spring pushes a ball like a pinball plunger, something like that, then you set it equal to the kinetic energy which the ball will have after the spring energy is converted into moving the ball. And if you know the mass of the ball, you can figure out how fast it is. And then once you have that, if you want to, you can say, well, how far will it roll up a hill? And for that, you use the equation for potential energy. So if you know how much kinetic energy it has, you can, and you know the mass of the ball, you can figure out how high up a hill it will go before it will stop and start rolling back down again. So you just use whatever term you have for the type of energy you start with, and you set it equal to the type of energy that it turns into. And that's all there is to it. And all your homework problems are basically using that principle. So let me show you something else which is kind of interesting that you may appreciate. We spent a lot of time with kinematics about the d equals x naught plus v naught t plus 1/2 at squared. All these big ugly annoying equations. Well, when you understand conservation of energy, you can do away with a lot of those. So let me give you an example of that. Say you, let's see, we've got the side of a building here, and there's a balcony, and we have a person standing up on the balcony behind a nice, safe guardrail there. And we're going to say that this is, let's say, 14 meters up. Okay, I'm just kind of picking a number out of the air for that one. And our person up here on the balcony is going to drop a ball, and the ball is going to fall all the way to the ground. And we want to know how fast is the ball moving when it hits the ground. So V final, what is that? Okay, now, and yes, this is 14 meters all the way up to where the ball is. So we're going to keep it simple here. Now, you can do this kind of problem using the kinematics equations, and you've done it before. But let's see how much easier it is when we use the energy idea. So the type of energy that it has when it's at the top, just before it lets it go, this is all PE, potential energy. And at the bottom, just before it hits the ground, it's all kinetic energy. So we can set those equal to each other. So we have mgh, that's the potential energy equation, is equal to 1/2 mv squared. That's the kinetic energy that it has at the bottom when it converts one to the other. Now, as you'll notice, the masses happen to cancel out. The mass appears as a term in each equation. So it actually doesn't matter what the mass of the ball is when you drop it, because all objects accelerate at the same rate, so they're all going to have the same speed when they hit the ground. So yeah, it's kind of interesting if the masses drop out. So this means that GH is equal to 1/2 V squared. And so G is 9.8 times the height, which is 14 meters, and that is equal to 1/2 V squared. Now we can use a calculator here. So 9.8 times 14, multiply that by 2, take the square root, and it comes out to be, that's wrong. I hit a wrong button someplace. 9.8 times 14. There we go. Yeah, actually, that is right. Times 2 equals 274. We take the square root of that. Okay, yeah, I did hit a wrong button. So 16.6. So V is equal to 16.6 meters per second. And if you feel like punishing yourself, you can run this through with the kinematics equations, and I assure you, you'll get the same answer. So this is a much simpler calculation. And again, it comes from the idea that the potential energy at the top is equal to the kinetic energy at the bottom. Now, if you're uncomfortable running it without masses, what I would recommend is you just choose a mass of like 2 kilograms, because 2 times 1/2 comes out to be 1, and the mass kind of cancels out, at least on one side. But yeah, you don't even need to know the mass. Okay, let's run a similar problem here. Well, let's do a similar problem. Suppose instead of just dropping the ball, what if you throw the ball downward at 5 meters per second? Okay, so rather than just dropping it, he flings it downward, and the initial velocity is 5 meters per second. Now we want to know what the speed is at the ground. And now you might think, well, okay, if it starts with 5 meters per second extra, it's probably just going to be an extra 5 meters per second. So it's going to be 21.6. Is that what it's going to be? 21.6 meters per second. 5 meters per second more at the top, 5 meters per second more at the bottom. What could go wrong? But let's check to see if that actually works. So this time at the top, we have some potential energy and kinetic energy. And then that's going to equal the kinetic energy at the bottom. So here we're going to have PE plus KE at the top is equal to the kinetic energy at the bottom. So we have MGH, that's the potential energy, plus the kinetic energy at the top, which is 1/2 m times 5 meters per second squared, plus, and that is equal to 1/2 mv squared at the bottom. Now again, mass shows up in every term, so that's going to cancel out, and we wind up with GH, so 9.8 times 14 again, plus 1/2 times 5 squared, that's the kinetic energy term at the top, and that is equal to 1/2 v squared at the bottom. Crunch some numbers, and we get 9.8. That's what I did wrong. My decimal point's not working well. 9.8 times 14 equals, that's 137.2 plus 12.5, because that's half of 25, equals 1/2 v squared. So that is plus 12.5. We get 149.7 times 2 equals v squared. So we multiply that by 2, take the square root, and we wind up with 17.3 meters per second equals v squared, which may be surprising. That's a little counterintuitive. Turns out you did not gain a whole lot of speed at the bottom by throwing it downward at 5 meters per second to begin with. You only gained less than 1 meter per second. And the reason is because when things go fast, they have a lot of kinetic energy. And when they go relatively slow, they have a relatively insignificant amount of kinetic energy. So the amount of energy that you added by throwing it downward at 5 meters per second wasn't a whole lot compared to the amount of energy in the form of potential energy. So it didn't add much energy at the bottom, so it didn't increase the speed very much. Yeah, so kind of a surprising thing. Now, there's a lot of ways you can run this. You can also run it where you know the speed. Somebody down on the ground will throw a ball up to the person on the balcony, or a box of candy to their girlfriend or something like that. And you know the height, and you figure out, well, how fast is the thing going as it passes the person on the balcony? That's another way you can do it. So again, it's just kind of setting terms equal to each other and solving for what you don't know. All right, all of the homework problems are this style. I mean, not necessarily this problem, but it's this idea of setting energy equal to each other. I think you'll be able to handle it. So, good luck with that one, and we will see you next time.